you have to be sort of present for the entire session, or the majority of the session at least, in order to be eligible for this credit. And also, this is brought to you, or this presentation is brought to you by the Midas Elite Center. Here at Midas, we specialize in giving sort of several types of presentations out to engineers for professional development hours. This is one of several, and I'll talk about other opportunities you have to take advantage of these courses later on. Okay, so first I'd like to introduce our speakers. So our speakers today will be Konstantinos Singros and Alan Popel from Langen Engineering. So just a brief introduction for Konstantinos. He's currently a project manager at Langen in the New York office, and he received his master's degree in structural engineering from the University of Athens, and he received his PhD in structural geotechnical engineering from the City University of New York. Okay, and also Alan Popel, I believe, has a small part in this presentation as well. He's currently the senior principal in Langen Engineering, and he received his master's and as well as his bachelor's degree from the University of Illinois at Urbana-Champaign. Okay, so then a brief introduction of the Kingdom Tower. Currently, the tower is still under construction, and it's located in Jeddah in Saudi Arabia. And the design height is 1 kilometer, or 3,280 feet, and when completed, it will be the world's tallest building at an estimated cost of $1.23 billion. And it was constructed or designed using a pile raft foundation, which was designed with Midas GTS, which is a 3D finite element software specifically for geotechnical and structural design. So Kostas and Alan will be going into greater detail about the design of the pile raft foundation. Okay. So once again, the foundation was designed heavily using Midas GTS, which provided several advanced solutions for the pile raft foundation. So for those of you who have questions about Midas GTS, just save those for later. You can learn more about the program and our software programs in general at midasuser.com. And if you have any questions that you'd like to direct toward us, feel free to email us at midasoft@midasuser.com. Okay, so now that I provided an introduction, what I'll do is I'll turn the time over to Konstantinos Singros, and he'll give you the lecture on the foundation of the Kingdom Tower.
Hello everybody, good afternoon. My name is Konstantinos Singros, and today we will be presenting a case study on the foundation design for the Kingdom Tower and how we use finite element methods to do the design, along with my colleague Alan Popel. This is the obligatory copyright material slide. Today's learning objectives will be to understand what in-situ and laboratory tests are important to select design parameters for this magnitude of project. The steps to develop to model a deep foundation using the finite element method. The interaction process between the structural engineer and the foundation engineer. And the thought process to select the length of deep foundation elements. This is a rendering of the tower. We can see on the left also part of the podium, part of the foundation. It's going to be a very slender tower with a height to width aspect ratio of 12:1. And just to put things in perspective, the spire is approximately as high, as tall as the Chrysler building in New York City. When we talk about the subsurface investigation, the subsurface conditions at the site, laboratory testing, electrical resistivity testing, and in situ full-scale testing that we performed at test files and this is the boring location plan that shows the outline of the tower and the locations of the borings performed at the center and the legs of the tower. The boring at the center was extended to 200 meters below ground surface, which was at the time the deepest boring in Saudi, which is where the Kingdom Tower will be located. The general structure has conditions consist of a superficial layer of sand 2 meters thick, followed by coralline limestone, which is up to 50 meters thick, and mudstone gravel layer over compressible decomposed sandstone, gravel conglomerate layer, and finally the more competent sandstone layer at around 120 meters from the ground surface. Limestones that were recovered. You can see the impression of the seas and multiple colors. And this is what the very completely weathered sandstone looks like at a depth of 85 to 90 meters. We performed unconfined compression strength tests for a number of samples, and we showed that typically the strength range from about 1 to 3 megapascals or about 10 to 30 tons per square foot. Of interest is the area between 70 and 90 meters below ground surface, where there was a drop in the strength of the material, and it was about half a megapascal or 5 psi. We performed a series of tests to develop
Hello, Costas. Can you hear me?
Yes.
Yeah, I'm sorry. I'm getting a couple of complaints here about the audio. Apparently, do you think you could speak a little closer to the microphone? Several engineers are having a little trouble hearing you.
Is this better?
Hold on. So yeah, for those of you who are having some trouble hearing, Costas will try to speak a little closer to the microphone. So just type in to the chat box and let me know if you can hear him better. Okay, no, not yet. Okay.
I'll try to talk
Okay.
a little louder. So we performed a series of in situ laboratory tests to determine an appropriate design modules of the formation for the different soil and rock layers. We used information from instrumented unconfined compressive strength tests, pressure meter tests, triaxial tests, and tests we used information that was back calculated from in situ load tests and information back calculated from very low strain tests, for example, information coming from shear wave velocity test. And we saw that an appropriate range varied from the top, or the top 30 to 40 meters, between 400 and 600 megapascals, and dropped significantly at the zone of decomposed sandstone. We examined not only overall the tests below the tower, but also individually the tests below each leg of the tower to make sure that there is consistency among the results, and we took that into account when we selected our parameters. These are pictures of the load tests at the site. To the left are pictures of the wholesale testing that was performed at port piles, and on the right side are pictures of the footing load test that was performed on top of the coralline limestone layer. This is the result of the footing load test that showed that for approximately settlement realized bearing pressure of about 3.3. I'll do my best.
Okay, thank you.
So this was a typical configuration of the O-cell testing, where we used two tiers of O-cells to better differentiate between the response of the torque of the ball pile and the response of the side shear. These are approximately 1.5 meters in diameter piles, and we are going to see that for the length of about 45 meters, the capacity was about 35 kilo meganewtons. So these are some typical results of the O-cell testing, and this is very useful information, especially when we go to do later our finite element modeling to model the interface between the rod and the pile. We were able to substantiate an ultimate side shear resistance of about 500 kilopascals using polymerous drilling fluid. We performed these tests for various lengths and using various drilling fluids. Some of the early analysis. This plan shows the locations of the shear walls marked with red. You can see that there is an absence of shear walls at the middle of the tower, and the load takedown for each area of the wings at the middle of the tower, we noticed that it was more or less equal to about 200,000 tons. So overall, we noticed that the foundation was loaded uniformly. Some basic foundation statistics. The Raft area that we ended up using is about 3,200 square meters or 35,000 square feet, with a total gravity load of 860,000 tons, applying a uniform pressure of 2.65 megapascals, close to 30 tons per square foot, and supported on 275s with an individual initial capacity of 32 meganewtons, about 3,600 tons. Some of the considerations for selecting the foundation, early on we realized that the tower weight was too great to be supported by a shallow foundation. So we had to go with a thick foundation using either board piles or barrettes. Barrettes are essentially piles with an orthogonal cross-section. We had concerns of the presence of gravel below the limestone layer that would interfere with the installation of deep foundation elements, the presence of a softer decomposed sandstone, and the high depth of the coated sandstone. Regarding the capacity of the limestone, just indicatively, we estimated an ultimate carrying capacity of about 2.5 megapascals, and using the various factors of safety for different types of coating, we ended up with an allowed bearing capacity of about 830 kilopascals for gravity loads. When we compare that with the 2.65 megapascals we mentioned earlier, we can understand why shallow foundation is not feasible. Regarding the pile lengths, for a 45 meters depth, we could achieve a theoretical allowable capacity of 42 meganewtons for gravity. We understood early on that this was not a carrying capacity problem, but it was going to be a differential settlement type of problem. So we had to start with some calculations and perform some initial block analysis using the finite finite elements, and then continue with more appropriate finite element analysis using a one-step procedure, which is the regular way, and the multi-step or an iterative procedure, which we're going to be talking about. For the kind of calculations, there are a couple of methods available out there. One is a typical two-thirds, one-third method, where you estimate the stress at two-thirds of the depth and use elastic solutions to estimate the settlement. The other is the Baker method, which uses similar assumptions to estimate the settlement, the total settlement of the model at the top of the foundation. The block analysis, essentially, instead of taking the time to model 270 files by themselves, because they were close in space, you could consider the reinforced rock area as a block, attribute the appropriate elastic properties to the block, and then do your analysis. Now we're going to talk about the conventional one-step method for finite element analysis. Essentially, we're talking about the file graph foundation consisting of 270 bond files, 1.5 meters in diameter, supporting a 4.5 meter thick structural raft, which at some points becomes thicker, with some initial file lengths of 45 meters and 75 meters. And we also consider another scheme of barrette foundations, 1.2 by 2.8 meters. Early on, we understood that for this magnitude of the problem, we needed to find the critical parameters and focus on defining those parameters well, that influence the problem the most. So one of them was the thickness of the raft. Another was the locations and geometry of the files, which is mostly the length of the file that makes a difference. The soil and rock modules of the formation, and then the method of construction, what kind of drilling needs to use, and how that interacts with the file rock or file soil interface. In typical finite element modeling fashion, the input consists of defining the geometry and the material properties of the raft, the files, the soil and rock layers, having appropriate elements such as choosing volume elements, area or line elements for the various parts of the method, defining the boundary conditions, and defining the loading, the construction staging, taking into account the set weight of the foundation and the tower loads. This is what the finite element mesh looks like. To the left, it's a box of 200 by 300 by 300 meters. And to the right, you can see that inside this box is described the file graph foundation. The raft has 3 wings that are approximately 15 meters wide by 60 meters long. And again, the files are 1.5 meters in diameter and they vary in length between 45 and 75 meters. The mesh becomes finer as you get closer to the foundation and becomes coarser as you get away from the foundation. Now, you can see the various layers described, the coronary limestone layer and the rest. Typical soil and rock constitutive models consist of the elastic, which is the easiest model because it only needs 3 parameters, and moving to more complicated models like the board long, where you need to assign also a friction angle and the cohesion value to your layers. A modified multi-normal soil handling model is modified multi-long and soft soil models were not used in this study because there was no need to. And the multi-long was used along with the food ground, which is a model for rock. Typical structure models for the raft you can use an elastic with volume elements, or you can use two-dimensional plate elements. For the piles, you need to talk a little bit more. You have a little bit more of a selection. You can use volume elements with or without an interface, beam elements with or without interface, and embedded beam elements with an interface. So the best model is to use solid elements with an interface. And this is shown on the left, but for foundations that have more than 30 piles, it becomes very cumbersome to model, and then the computer model takes too long to run, and it crashes if too much. An intermediate situation is the beam solid connectivity model, where you have the pile described as a beam and not with volume elements. For situations of with large numbers of piles, the model where the pile is modeled with a beam, and there's a special interface between the pile and the soil is used. This is the best model, and it's sufficiently accurate and can handle a large number of piles. This was what was used for this problem. Typical loading conditions, the soil and foundation self-grade needs to be included. Column and wall loads can be modeled as point loads, line loads, and pressure loads, and the foundation construction stages need to be modeled. For this project, there was no basement, so the construction staging was simple. Initially, we used two different computer programs with two different users to compare against each other, and the results between the two different programs were very similar. We continued with initial finite element results. This is for the scheme using 45-meter piles, and we saw that this scheme was yielding a settlement at the center of the foundation of about 180 millimeters and differential settlements of about 60 millimeters. A similar model that has 75-meter piles at the center was able to limit the anticipated settlements to 160 millimeters at the center, and the differential settlements, which were of more concern, to about 50 millimeters between the center and the edge of the foundation. The finite elements can also provide bearing pressure coatings, such as those depicted here. And we can see that stresses are higher at the edges of the raft. And there is a little bit of concentration at the bottom. This is a cross-section that leads in the table all the important properties used to model the different layers. And this is a very useful way to present the analysis to a peer review team, so they can easily check their assumptions and model do a model for themselves. Now, the structural engineer's train of thought for this project was that we have a uniform loading, approximately uniform loading, as we saw earlier. About 200,000 tons per leg. And a rigid foundation based on the fact that it was 4.5 meter thick raft. As a result, we were expecting uniform settlement, which would result in a uniform single K value, which is a spring or a volume substrate reaction. And eventually would result in uniform pile loads and uniform wall stresses. These were the results that the structural model was obtained. However, as geotechnical engineers, we are aware that if below there is a footing, to obtain uniform settlements below the footing, the stress distribution cannot be uniform, but it has to be non-uniform with higher stresses at the edges. This is what the theory of elasticity predicts. And accordingly, there cannot be one single K value that can model this behavior. There has to be at least two different K values to model what happens at the center and at the edges. We started noticing some deviations between the results of the structural model and the geotechnical model, and those differences were mostly at the pi loads at the wings of the foundation. We noticed that we were getting very high loads at the piles at the edges, whereas the structural engineer was obtaining uniform loads. To check whether if this is a fluke, we made the fluke where with the process we plotted with the pi axial load for each pile versus the distance of starting from the center of the raft going outside to the legs. And you can see that the pi load started to increase, and to check that we also plotted the vertical stresses of the coralline limestone along one of the legs of the foundation, and we saw that indeed they follow the same trend. They start increasing as you go towards the end. And this is consistent with the theory of elasticity. So we knew that the structural model and the geotechnical model were giving, they were not capturing the effect correctly. The response of the soil foundation superstructure system was not captured accurately, and the foundation strings needed to be refined. On top of that, the effect of the superstructure stiffness needed to be better captured by the geotechnical. That led us to change our approach, and instead of using a one-step procedure, we will talk about what it is exactly, we used a multi-step procedure. Let's start with a simple case of a Raft foundation, no parts. The structural engineer provides the following loads to the geotechnical engineer. The geotechnical engineer does the finite element analysis, predicts settlements, and provides weaker strings to the structural engineer. The structural engineer runs his or her model with the new strings, predicts foundation settlements, and then there is an iterative process to update the weaker strings until the settlements between the structural model and the geotechnical model converge. This is one-step process if the structural engineer only provides the pulling loads to the geotechnical engineer one time. The multi-step process would be if at the end of the converged solution, the structural engineer checks the column loads and sees that if they see that there are changes in the column loads that were caused by the weaker strings, then supplies the geotechnical engineer with a new set of column loads. And then this cycle gets repeated again. So this is the process for rafts. If we have a foundation that is combined pile raft, then in addition to the raft settlements, we would require convergence between the geotechnical and the structural model on pile loads, the load sharing between piles and subgrade, the column or wall loads for the structural engineer between iterations, and the iterations they will continue until the wall loads between successive iterations are below a certain percentage. For this project, high accuracy was required, so a 5% tolerance was set. Now, for the 45-meter scheme, when we started following this procedure, we saw that it required many iterations, and the results did not always converge. To achieve better convergence, it required that we divide the raft in many small areas and provide sprints for all those areas. The structural engineers started predicting in this model high stresses on the walls, and overall the stress level in the team increased considerably when we started doing this method. This is to give you a better idea of what was happening. At the top are the results of the geotechnical model, and at the bottom are the results of the structural model. So for the first iteration, we had this sort of settlement contours, and we provided the strings to the structural engineer, who then ran their model and predicted this settlement contour, which did not match our settlement contour. So they ended up giving us a new set of whole loads. We reran our analysis and predicted a new settlement contour. And we followed this method. And as you can see, for this type of foundation with 45 meters meter long pipes, the settlement contours did not appear to converge. This is a plot that shows that the stress at the wings of the structure starts to increase, and compared to the stress at the walls of the center of the building, the wings were about more than 2 times higher, and this could not be tolerated by the structure. So this led us to revise our foundation scheme. So what we did was we compared the foundation response without any iterations. So we started from basics, just one set of ball loads, and we compared the foundation, the settlement contours between the 45-meter scheme and the scheme that had longer piles at the center. And we saw that the 45-meter scheme leads to a significant redistribution of ball loads, whereas a deeper scheme leads to a minor redistribution. So it was an easy choice to make. Either we would have to increase the stiffness of the foundation to limit the redistribution of stresses in the structure, or the structure would have to change stiffness, which was not preferred. So we decided to increase the stiffness of the foundation. Once we started increasing the stiffness of the foundation, the relative distribution of the pile axial loads started to change. So instead of noticing that the axial loads at the edges are much higher than the axial pile loads at the center of the raft, they started becoming more uniform. Then there was the question of where do we stop the piles? And this is a good representation to see what options we have. To try to put the piles inside the competent sandstone layer would lead to very high lengths, and it would not be feasible to construct. If we tried to stop them at an elevation between 110 and 125, we would create a hard spot at the piles, which was also not desirable. If we tried to put the piles inside the compressible decomposed sandstone, well, obviously that would not be good because we would have increased settlement. We knew we needed to increase the length of the piles beyond the typical 45 meters inside a relatively competent limestone. So we ended up using lengths of about up to 105 meters to stop the piles at the center in this layer. we had a tapered pile foundation starting from about 45 meters length, 45 meter length, and going all the way to 105 meters at the center. And once we started using a steeper foundation, then convergence between the structural model and the geotechnical model was much more easily achieved. In this graph, we can see how the settlement volumes progressed from initial set of column loads to the final set of column loads. And we can see that settlements did not change all that much. However, there was a big difference in the wall loads. The walls of the wings, here, here, and here, ended up increasing in load by as much as 50% during the first iteration, which shows how sensitive this analysis is to the stiffness of the superstructure. Once we compared, we showed that in between iterations, the changes in the wall loads were very small, which showed that we have achieved the convergence. We provided to the structural engineer a set of 270 different pile springs and a set of 16 different area springs. And there was a big range in springs between 200 and 430 meganewtons per meter, and an even more pronounced change in the area springs between 1.5 and 30 meganewtons per meter cube. And this is what it looks like to have convergence in settlements between the geotechnical model on the left and the structural model on the right. You can see that the models are very close. The difference in settlements at the locations of the piles were all within 5 millimeters between the converged models. And the difference in pile loads between the converged models were between 0 and 2 meganewtons. Using the stiffer foundation with the higher lengths at the center of the foundation was able to alleviate some of the stresses on the walls on the wings and have a ratio from the previous 2.2 compared to the center wall stresses to just 1.6, which was something that the structure could handle. And as the final remarks, the geotechnical model typically governs the ground settlements. And this iterative process or multi-step process gives an insight on the distribution of column volumes. The geotechnical engineer does not have to attempt to model the stiffness of the superstructure. If the geotechnical engineer attempts to do that, you will see that you will not be able to reach a convergence with the structure. This redistribution of column and wall loads is more pronounced when the superstructure is very steep compared to the foundation. So this redistribution is not typical for all sorts of buildings that are out there. It's more pronounced for structures that are as rigid as this tower. The redistribution necessitated to stiffen the foundation by using longer piles under the center of the raft. And the longer piles are not needed for an increased soil bearing capacity. We have one with a 45 meter steep. They are needed to alleviate the increased outer wall stresses in the superstructure. With that, I would like to thank you and turn the control back to my colleague.
Oh, hey, Kostas. So thank you for your presentation. I understand that There's some engineers here who have some questions for you. Since we have some extra time here, let's just have a sort of 10 to 15-minute question and answer session. Would that be all right?
Yes.
Okay, perfect. So actually, I'm going to go and make you the presenter again in case you have to in case you have to go back to your slides. So just give me a second here. Okay, and then make sure that, okay, perfect. So I know that several of the engineers here sort of typed into the chat box to ask some questions. Do you have access to the chat box right now? Okay, that's okay. I'll read them off to you just to make things easier. So first, one question that I see here is, was the structure designed for lateral loads such as earthquake and wind loads? If so, how does the pile raft foundation respond to such non-uniform loads over the mat area?
The structure was designed for wind loads and was designed for earthquake loads. The wind loads governed the response of they governed the design, and were modeled with the finite element model. It's just that this was not shown in this presentation. A pseudostatic lateral load approach was followed, and pile loads and deflections were checked to make sure that they're satisfying geotechnical concerns and structures. Does that answer the question?
For his response here. Okay, no response yet, but yeah, if you have a follow-up question to that, just type it into the chat box. So I'll just read the next question here. It's please explain what initial pile length means. So I think at one point, sort of earlier in your presentation, you sort of discussed initial pile length. So the engineer just wants to know, I guess, what exactly that means.
Initial pile length means that we did not start with the final configuration where we were trying to figure out what were the lengths of the piles. Initial pile length was a length of 45 meters, which was approximately the thickness of the coralline limestone layer. So we were using as much of the capacity this layer could provide to the piles, and we were checking to see if it's enough to satisfy the design requirements.
Okay, thanks, Kostas. So I have another question here. How did you estimate the pile's shear and normal stiffness from the results of the OCEL?
Okay, so for finite elements, if you're going to use the embedded pile option, you have to describe the soil or rock pile interface. And what you would do, a neat way to go about it would be to perform an OCEL test and have a graph which displays the unit sites here versus the average zone movement. In that case, the initial slope would be the slope that you would prescribe in the soil pile interface, and the plateau, well, an appropriate plateau would be where you define your ultimate site shear. Now, also for normal stiffness, you would typically need to do a lateral load test and back calculate what that normal stiffness would be. these offset tests are used to give the information for a vertical load.
Okay, thanks, Kostas. So I have another question here. So was there a comparison in the analysis between Midas GTS and other software outputs?
I'm sorry, what is the comparison between the two programs?
Yeah, so did you compare like the outputs of Midas GTS to any other sort of program? So like, for example, if you used another program to do the analysis, did you compare the results?
Correct. We wanted to make sure that we had at least one independent way of checking what the results, if the results we were getting were accurate. So we modeled the same foundation with the same loading using two different engineers and two different pieces of software, Midas GTS and classes. And we saw that overall the results were really close to each other within 10% of settlements, which if you think that there are two completely engineers that model with two completely different programs this foundation, it's pretty consistent.
Okay, thanks. So we have time for just two more questions. So I see just one more. And if anybody has any further questions after the session closes, just email them to us and we'll get back to you later. So here's the next question. It's how far has construction progressed and how does it match your predictions?
I believe half the piles have been constructed up to date, and how it matches predictions, we do not have that information yet, so I cannot know. Hopefully it matches very close.
Okay, and then just one last question. Why was the 45-meter depth scheme, why was that selected in your analysis?
It was selected, what was driving the length was selecting the geotechnical capacity. So we figured that for this kind of diameter and this kind of length, we had sufficient geotechnical capacity to support the tower, which was true, but what happened was that the settlement requirements were not satisfied. And that's why the 45-meter scheme, even though it was appropriate from a capacity point of view, was not enough to satisfy the settlement, the differential settlement requirements.
Okay, thanks. So that'll be it for the question and answer session. Thank you for your questions. And once again, if you have any further questions, either for myself or for Kostas, just email them to us and we'll get back to you later. So Kostas, can you just switch me to the presenter real quick, and I'll just give the closing points of the session.
So how was Angela Kim?
Okay, so thanks again everyone for taking the time to attend. I just want to make one last announcement before we wrap up. We will be having a follow-up session, or just actually a next session next week on stage excavation and deep foundation design using finite element modeling, specifically with Midas GTS. So for those of you who are interested, more specifically in how GTS can be used maybe for your own projects, we highly encourage you to attend the session. We'll be sending out the invitations early next week to give you some more information about it. So just mark that down on your calendar. Next week on the 26th, Thursday, 3 p.m. Eastern Standard Time, we'll meet again to sort of discuss the finer points of Midas GTS and how it can be used specifically for this type of project. Okay, so thank you once again for your attendance. We'll make sure to get the PDH certification out to you guys soon. Once again, further questions can be directed to midasoft@midasuser.com. Okay. So thank you again, and we hope you all found this presentation useful. You take care now.